Here we go. All right. So the request was to go over the properties of relations. So we got reflexive, and the way I describe reflexive is if a relation is reflexive, then this condition has to be true. So it's good to understand what the expression is saying. The expression says for everything in X, okay, and the relation is defined over X. So for everything in X, that thing has to relate to itself using R. So that's the requirement for a relation to be reflexive. Now, can R contain other elements? Absolutely. So this is only defining the minimum in order for a relation to be reflexive. So do we have any questions about reflexive? So if X has A, B, and C as elements, okay, then R must have AA, BB, and CC as elements. When I say AA, it is a two-tuple, where the first element is A and the second element is also A in a two-tuple. So AA is one element, BB is an element, and CC is another element of R. Well, that's what I said, but I can write it out. Okay. So if we use X, and say X has A, B, C as elements, and R, if I want R to be reflexive, then R has to be a superset of the following: AA as an element, BB as an element, and then CC as an element, in order for R to be reflexive. Is that okay? Because the idea of being reflexive is every element of a set has to relate to itself through the relation. So if one element is not relating to itself, then it is no longer reflexive. Is that okay? Are we good? Okay. So let's look at the second one. The second one is symmetric, or symmetry. So if we look at the mathematical definition of symmetric or symmetry, it says, go ahead, I have two variables, E and F, and you can choose anything in X to be E and anything in X to be F. So they can be the same thing, they can be different things. But no matter how you choose values for E and F, the following has to be true. Let me zoom in, because without zooming in, the equation is a little harder to read. There we go. So what has to be true? Well, what has to be true is EF as a two-tuple in R, if and only if FE is also in R. So if one is missing, the other one has to be missing. If one is present, the other one also has to be present. Is that okay? So the key here is the if and only if symbol, or equivalent symbol, this thing here. Okay? So what this thing says is if the left-hand side is false, the right-hand side has to be false, and then the other way around. If the left-hand side is true, the right-hand side also has to be true, and the other way around as well. That's why it's also called if and only if. So now going back to our example, continuing to use X equals to ABC, then the simplest R that is symmetric is this. If R is empty, it is automatically symmetric. Are we good so far? Because nothing is related to anything, right? So if you choose, A as E and B as F, EF is missing from R, but so is FE. So that's why it is automatically symmetric. Yep. That is true for any set X. That is correct. Why would it not be? I mean, that's the question. Why would an empty relation not be symmetric? Okay, but I can. well, I can think of an argument, okay? So the argument is, if you want a relation not to be symmetric, then you have to find a particular way of choosing a value for E and a value for F, such that whatever is in between, here, is not true. So one is here and the other one is not. So if X is empty, then you have no way to choose elements anyway. So that automatically makes both the left-hand side and the right-hand side true. Is that okay? Because you can't even choose E and F. So let me show you some examples of what is symmetric and what is not. So this is symmetric. Now R is AA, BB, CC, which makes it reflexive. It's also symmetric, right? Because if AA is in R, so is AA. I just so happens to choose the value A for both variables E and F in the expression. Does it make sense? Let's go back to the expression here. So if E is A and F is A, okay, then AA is in that particular R. But you know what? So is AA. Is that okay? But, okay, so does this mean, something being reflexive is automatically symmetric? Well, that is not the case. Because now I can give you an example like that. Is not symmetric. So in this example, if I choose A to be E and B to be F, then EF is in R, but FE is not in R. But in order for a if and only if to be true, either both sides are true or both sides are false. In this case, one side is true, the other side is false. So as a result, you can no longer claim the for all anymore, because I can find one example where the condition inside here is false. Is that okay? Well, how do I make it symmetric again? So to make this symmetric again, all you have to do is to either remove AB in it, or you can introduce BA in it. Then it becomes symmetric again. This is once again symmetric. Is that okay? Yep. Uh-huh.
For empty relations, is it true depending on the set X that you pick?
For reflexive. So if X is empty, then the empty relation is also reflexive. But for any non-empty X, then an empty relation cannot be reflexive. Yeah. So are we good so far? With reflexive and symmetric. Now those terms are very, yeah, go ahead.
I just had a question. Can you have a set that is not an empty set that can be both reflexive and antisymmetric?
Reflexive and antisymmetric.
Yes, that's not an empty set.
Okay, so we'll get to antisymmetric next. So right now we're just focusing on reflexive and symmetric. But keep that question in your head, okay? So are we good with these two? Okay? So the next one up is transitive. So transitive, according to this definition, basically says, I have three variables now. Now, three variables means, pick something for E, pick something for F, pick something for G. They can be the same thing, two can be the same, the other one can be different, and so on, okay? But regardless of how you choose the values of E, F, and G, this part has to be true. So that part basically says, if EF is in R and FG is in R, then EG has to be in R. But it's a one-way. It's not if and only if. This is a one-way implication. Is that okay? All right. So given this, Let's check out, what is transitive and what is not transitive as an example. So this time I'm going to choose something a little bit more complex. Have 4 elements in X. And in R, we will start with the empty relation. So is this R transitive? It's empty. And why is it transitive? Well, let's go back to look at the condition here. So I basically have to say, regardless of how I choose values for E, F, and G, this still has to be true. The implication still has to be true. But because R is empty, do you think A relates to B? Nope. If A does not relate to B, that means this element of is false, which means this conjunction is false. But if you have the left-hand side of an implication being false, what is the value of the implication itself? The implication itself is true. So you can basically use that argument for any way to choose values for E, F, and G because R is empty. Nothing relates to anything. Okay? So that's why by default an empty relation is transitive. All right, if that is transitive, let's check out this one here. It has AA, BB, CC, and DD, okay, which means it is reflexive. But in this case, I don't care about whether it's reflexive or not. It is also symmetric, but I don't care about whether it's symmetric or not. I want to know whether it is transitive. It is transitive, yes. Because you can't really apply the case where you find E, F, and G, where they're all different, and you can find that they chain. There's no chaining here. So that means no matter what you choose as E, F, and G, okay, the only way you can make this side true, you can make it true, but the only way to make it true is you have to choose the same value for E, F, and G. Okay, you can choose A for all of them because AA is in R, AA is in R, but guess what? AA is in R too. You cannot make it false. How do you make this thing false? When the left-hand side of the implication is true, but the right-hand side is false. So what you need to do now is to say, okay, we need different values, right? So let's see what the next example is, whether it is transitive or not. So this is transitive. So when I use is transitive, I'm not saying it is only transitive. I'm simply saying that it is also transitive. Okay? So do not misunderstand this statement. R equals to blah 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 is transitive. It's saying that it is only transitive, but it is not reflexive. No. In this case, it is also reflexive, it is also symmetric. I just choose not to include all of those because my focus is on transitive. Is that okay? Because I don't want people to misunderstand, that it is only transitive. Okay, so let's check out the next one. So R is AA, BB, and we'll just add BC here. Is that transitive? How can I make that condition false? You would ask. I would ask. How can you make that condition false? You cannot make it false. It is transitive. Because you can choose EF to be B, and then you can choose G to be C. But then you have EF, FG, right? But then you also have E, G also being okay, because EG is the same thing as FG. Is that okay? Sorry? Yeah. Okay, so this is also transitive. Okay, let's look at the next one. What if I throw in CC? Would that make it not transitive? it is still transitive. All right, so let's see whether this one is transitive or not. So R is this. And then I decide to choose, let's put CD in it too. Now it is not transitive. Yep, you will need BD to be in it in order to be transitive. But the way it is right now is not transitive, because I can choose B to be E, C to be F, D to be G. Then I can make EF in R, FG, EF in R, FG to be in R, but EG, BD is not in R. So I can make the left-hand side of the implication true, but the right-hand side of the implication false. And that is the only one case in the implication where the implication itself is false. So are we good so far? All right, cool. So are we good with whether something is transitive before we move on to anti-symmetric? Yes?
How come? So, for something where you have like AA, BB, BC, or line 14, why couldn't you say like if you wanted E and F to be A, and then G would be C? Like AC isn't in the relation, right?
Okay, say that one more time so I can actually write it down.
So if you have E and F to be A,
E equals F equal A,
and then G would be C.
G would be C. Okay.
AC is not in the
But,
relation, right?
yeah, but FG is not there either. So the left-hand side of your implication is false already. I don't care about the right-hand side. Yep.
What if for line 14 you used B for E and then C for F and G?
Okay, say that one more time. B is E. E has B, F has C, and then G has C as well. Okay, so let's see what happens here. You're missing CC. So in this case, the left-hand side of the implication is already false, because BC is in R, but CC is not in R. So I don't even care whether BC is also in R, which turns out that it is. But CC is not.
Okay.
Yep. So are we kind of okay so far? Okay. All right. So let's move on to anti-symmetric. So the first thing I want to kind of clarify is the word anti-symmetric is not to say that it is not symmetric, okay? Because if not symmetric is the same thing as anti-symmetric, then we would not need that property. So that means it should be possible to make them both false or both true. Is that okay? All right. So let's move on to the definition first. So when you're studying or when you are in the test, trying to answer a question, I personally would go straight to the definition first, because that's the basis, and that's where we start reasoning. So you definitely want to make it so that it is relatively easy for you to find the definitions. It's open book and open notes. So that means, bring your own notes. If you have been taking notes, you can prepare, a sheet of paper or several sheets of paper just for the exam that has everything condensed. All the definitions, all the terms, just on a clean sheet of paper. Because my notes is kind of stuff is sprinkled around, and sometimes you have long proofs in between and whatnot. So if you want it to be clean and easy to locate stuff, you can have your own, kind of index of, definitions and whatnot. So let's start with this definition here. So once again, we have implication, which is a one-way thing. And then the only way to make an implication false is for the left-hand side to be true, but the right-hand side to be false. That's the only time an implication is false. So unless you can find a case to such that the implication is false, then the thing is true. That's one way to look at it. Is that okay? So when you read the definition, it basically says choose values for E and F in any way you want, as long as the value is in the set X. If EF is in R and FE is also in R, then E and F must be the same. That's what it says, right? So this means the only way to make it false is for EF to be in R and FE to be in R, but E does not equal to F. That makes it false. Is that okay? But for everything else, it's going to be true. So keeping that in mind, let's switch to our example, and let's see if we can display both at the same time. Oh, okay. Turns out we do have enough room to do it. Okay. So once again, this time we can choose a simple one, like X only has A, B, and C, and then R is the empty set again. So is it anti-symmetric by its very nature? What do you think? A very quick clue is the implication, okay? Because in order for the entire implication to be true, you can make the left-hand side false. Then it's automatically true. So with an empty relation, nothing relates to anything else, right? So the element of has to fail. Doesn't matter what you put, on the left-hand side of the element of, because R is empty. Nothing is an element of R. So, and this is a conjunction, not a disjunction. If it's a disjunction, it's a little bit tricky because you can have at least one side being true, making the whole thing true. But because this is a conjunction, which means if at least one thing is false, the whole thing is going to be false. And since R is empty, there's no way to make the conjunction happy to be true. So the left-hand side of the implication has to be false, which means the implication itself has to be true. Is that okay? All right. Next thing. So this is anti-symmetric. So we'll look into, something that's already kind of typical. Now we know this is a few things, right? We know this is reflexive. We also know this is symmetric. We also know this is transitive. So now we want to say, well, is it also anti-symmetric? In other words, using this, can we make this implication always true? Or the converse is to say, is it not possible to make this condition false? Okay, that's the other way to look at it. So what do you think? We got relations, right? Okay, we got relations. And the relation has to be EF and FE. Well, sure we can do that, right? We can pick A to be E, pick another A to be F, then EF is in R, so is FE. We now satisfy the conjunction on the left-hand side. What about the right-hand side? Well, E and F are both A, so E equals to F is true. There's no way you can pick F and E so that you can make the conjunction true, but E and F are different according to this. Okay? Okay, so this is anti-symmetric. What about this? We got AA, we got AB, and then we got BC. And we also got AC. Okay. So what is this? This is not reflexive, right? It's not reflexive because BB is missing. CC is also missing. It is not reflexive. It is not symmetric because BA is missing. CB is also missing. CA is also missing. It is not symmetric. It is transitive because AB is there, BC is there, and then AC is also there. So it is transitive. But the question is it anti-symmetric? It is anti-symmetric. Because you cannot make that condition false. You cannot make this condition false. Is that okay? So let's check out the next one. The next one turns out to be pretty simple, just like that. What do you think?
No.
It is not. Okay, let's go through all of the other properties too. It is not reflexive, quite obviously. because none of the relations that we need for being reflexive is here. AA is not here, BB is not here, CC is not here. It is not reflexive. Is it symmetric? Yes, it is symmetric because AB is here, so is BA. But for all of the other things are missing, okay? So it is symmetric. Is it transitive? Because AA is not here and BB is not here, so it is not transitive. In order for this to be transitive, AA, BB have to be here too. Does it make sense? Because what I do is I say, what if E equals to A, F equals to B, and G equals to A again? Then EG is not here. And yet EF is here, so is FG. Okay? So it is not transitive. Is it antisymmetric? It is not antisymmetric. Because if I make EA and I make FB, then EF is in R, no problem. FE is also in R, no problem. But E and F are different. One is A, one is B, they are not the same. If I can find one case of choosing values for E and F such that this condition is false, then the for all quantifier is automatically false. Is that okay? So it is not antisymmetric. All right. So is that okay? And then partial ordering means that it has to meet 3 of these 4 requirements. In order for something to be partially ordered, it has to be, okay, it has to be reflexive. It should not be symmetric. It should be transitive, and it should also be antisymmetric. So if it meets those 3 requirements, it is known as partially ordered. But once it is partially ordered, it can also qualify as totally ordered if it also meets this extra requirement. So this is the requirement that separates partially ordering from totally ordering. Yes?
I wanted to ask about the trichotomy property, if it's supposed to be or E equals F as well.
Say that one more time.
So for the trichotomy property, is it supposed to be or E equals F as like a third case?
Or E equals F.
Yeah.
So to put parentheses around this whole thing and then do another or.
No, all in the one quantifier.
All in the same thing.
Because if you said like less than has trichotomy, you would say, okay, well, like...
Less than does not. Less than or equal to does.
I thought it did.
Nope, not less than. Less than or equal to does. So less than is not totally ordered, but less than or equal to is. Is that okay? All right.
Question.
Yep.
Can you give an example of something that is only partially ordered and something that is totally ordered?
Yes, the beer commercial.
Oh, right.
I was thinking that most people will walk away remembering the beer commercial, but not quite remembering why I used that as an example. Okay, so the beer example is partially ordered, but it's not totally ordered because we could not tell how to order smooth and not rich and not smooth but rich. So those two cannot be ordered according to the way we specify the problem. Okay. And therefore it is not totally ordered. If something is totally ordered, you can give me 2 values. I can always tell you how it relates one way or another. But in this case, I cannot tell you how it's ordered. So are we good so far with the relations? It's a super, well, I was about to say super quick, but it's not. It wasn't. It took about half an hour. But there were quite a few examples. Hopefully that helps. Are we good? Okay. If you guys can think of any other questions related to the exam, yes?
It is possible give us some number examples about ordering.
About ordering? Okay, well, once you use numbers and you use the usual comparison operators, it doesn't work anymore because numbers, integers, um, they are okay. I can give you examples that are not totally ordered. Easy one is less than. Less than is not partially ordered. It is not totally ordered using these definitions because less than is not reflexive. It's not meeting the requirement of being reflexive. So it automatically disqualifies as partially ordered, and anything that is not partially ordered is not totally ordered either. So when you throw in numbers, then certain things don't work as easily anymore because many operators are either not partially ordered at all, but those that are partially ordered is usually also totally ordered. All right. Any other questions? No other questions? All right. So if you guys can think of any additional questions, let me know. Until that time, we're going to move on and talk about resolution, which is where we left off last time. We were staring at this thing. Okay, so the first thing we want to do is really to say, what is it saying? Okay, we are looking, instead of looking at the pine needles, we look at the entire tree and go like, what is the shape of this tree, right? So the shape of this tree is basically saying that, oh, this implication is always true. Okay, well, a lot of implications can be always true, but what makes this one so significant? Well, what makes it significant is you started with two disjunctions. Okay, they're both true. One has psi and the other one has not psi. But when you look at the output of the implication or the result of the implication, it is missing that variable. That whole psi is completely missing. We only got phi and rho left. Is that okay? Are we good so far? Okay. I mean, let me point out what I'm talking about here. See how psi is actually here, on the left-hand side of the implication, but it's missing from the right-hand side. So that's the first thing that is kind of significant. The second thing that's significant is the format of the expressions are the same. Okay, when you look at the left-hand side, you can see how we have a disjunction, another disjunction, and they relate by conjunction. But the output is also a disjunction. Okay, so if you remember from the previous lecture, we redefined what is well-formed. Okay, so well-formed formula has to be basically a huge disjunction of either constants or variables or the negations thereof. Okay, this is giving us an interesting tool because what it's saying is the left-hand side of the conjunction is well-formed because it's a disjunction by itself. The right-hand side of the conjunction is also a well-formed formula. But what it is given us as a result of the production is also well-formed, even according to those modified rules of what is considered well-formed. Right? And then the third thing that's significant about this is the conjunction is a lot of times not actually represented because everything that is true in a propositional logic system, they're all true at the same time. So there's an implicit conjunction connecting all of those well-formed formulae that are already derived. Is that okay? Is that okay? All right. And unlike usual Boolean algebra, this always end up with a simpler expression. The expression as a result is always quote unquote simpler than what we start off with. Which basically means if you keep going like this, things can only get simpler and simpler and simpler until it becomes false. Hopefully. Okay? Is that okay? Because when do we simplify to false? So let me go back to this thing here, and I'll move this stuff out of the way so it's not distracting us. So I'm moving all of this out of the way. All right. So I'll give you an example. If P, Q, R, S, T are variables, is Okay, let me just use C++ symbols. Does this fit this particular template on the left-hand side of the implication? Yes. Okay. So we can then apply this implication, right? But then you say, but there's no implication here because P by itself is not a disjunction. Not P by itself is also not a disjunction. We do not have a match anymore. Well, that's easily fixed. You can always attach a or, not or false, right? Anything or false is anything. In other words, false is the identity of disjunction. Just like 0 is the identity of addition. Does it make sense? So now it meets that format, right? Because we have P on one side, the negation of P on the other side, and then we have phi. What is phi in this particular example? False. What do you think is rho in this example? It's also false, right? So that means the implication is just doing a concatenation of everything except for the variables, the variable that is inverted in one and not inverted in the other one. So now we end up with false or false. Is that okay? I mean, this is totally syntactic, okay? I'm doing a very syntactic pattern matching and go like, this is the template I'm looking for. This is what I'm given with. It does match the template. The template says we can manipulate the symbols a little bit and end up with this result. I'm doing the same thing over here, and I end up with false or false, which turns out to be false or false is false. Yep, it is an or. So it is false. Does that make sense? I mean, P and not P is implying false. It makes perfect sense, right? You cannot have both being true at the same time. In fact, because P and not P is false, the implication is always true anyway. But it does imply false. Is that okay? Are we good? Okay, so this is one piece of what we need to use when we are using CNF or conjunctive normal form. And then the other thing at the very end of the previous lecture that I mentioned is the completeness of CNF. What this means is if the only restriction that you have to express everything that you can express in Boolean logic is CNF, okay? Which means it is a huge conjunction. You have one single conjunction at the very end, and then the components that you're ending together, each one is a disjunction, but you cannot have nested things in the disjunction. Every disjunction can only consist of variables, negation of variables, and constants and negation of constants. Okay? So the question is, if I give you that much restriction, can you still express the equivalence of everything that you normally can express as a Boolean expression? That's the question. Is that okay? It's kind of like, instead of, giving you, 20 different types of syntactical or grammatical, structure in English, I say, we'll boil down everything to like 3, okay? Then the question is, can you still express every single concept that you were able to express when English has all of these 20 rules, when your grammar is simplified to only have 3 rules? That's the question. Are they equivalent? Can you express the same thing? And as it turns out, the answer is yes. So what we'll do is, instead of kind of talking through the quote-unquote algorithm here, we'll go do an example. So this rather complex, compound and nested and hierarchical Boolean expression, and I go like, really? This can convert to a CNF? Well, let's see what we can do with this. Okay. So you probably already know that it can, right? Because you can see all of these equal sign, and at the end we do have a CNF. Why is this a CNF? Because the last operation is an AND, and then the components you're ANDing together, each one is a disjunction, and the disjunction only involve variables and negations of variables. That makes it a CNF, a conjunctive normal form. Is that okay? So how does the derivation go? Well, this may not even be the best way to do the derivation. It is one way to do the derivation. Okay? So we'll start with the first and the second line. Okay? What is the change from the first line to the second line? Implication becomes not the first part or the second part. That's the definition of implication. So I personally like to get rid of implications first because then I only have the usual operators to deal with. What about from the second line to the third line? What did I do? I used De Morgan's law. Okay, very good. De Morgan's law is applicable when you have a negation on the outside of either an or an and. Okay, that's De Morgan's law. So when you apply De Morgan's law, it is kind of like distributing the negation to the inside. So you can see how this negation is now distributed here and also distributed here. But in doing so, you also have to change an or to an and, or if you start with an and, it becomes an or. That's basically De Morgan's law. Is that okay? All right. What about from the third line to the fourth line? What did I do? Simplification, right? Double negation of R. Yeah, it's just R itself. Pretty simple stuff so far. Are we good? Okay. What about from the fourth line to the fifth line? It is distribution. So I take this thing and I distribute it over that thing over there. Are we good so far? Now, distribution is a little bit interesting in Boolean algebra. It can distribute both ways. Because in arithmetics, you can only distribute addition over multiplication. But in Boolean algebra, it can go both ways with conjunction and disjunction. So in this case, I'm just, putting the and p together with here, and then putting the and t over there, and then I'm using the or in between to break them apart. Are we good so far? Okay. What about this crazy stuff from, let's see, this is the 5th row to the 6th row. That suddenly go like, plop. Yep. I distributed this over, that. So because we have 3 terms on one side and 3 terms on the other side, we end up with 9 terms. Okay, so here are the 9 terms, completely spelled out. So it looks really ugly, and that's why we need to simplify right away. So to simplify that right away, I think I did another distribution with this not p on the outside. So now we still have 9 terms, but each term now has up to 3 variables. And then I do some simplifications. Okay, so from the bottom up, the 4th line, okay, R or R is just R, okay? That's a fairly simple simplification. This one cannot be simplified. This one cannot be simplified. Let's see. This one cannot be simplified. This one is simplified because we have not Q or not Q. Therefore, it is simplified. Let me scroll a little bit here. This one is simplified to true because we have not P or P, right? So not P or P has to be true because P is a variable that can either be true or false. So if P is either true or false, then not P has to be the other one. One of those two, P or not P, has to be true. You only need one side to be true for an or to be true. So this simplifies to true. Then what about true or R? How come R is gone too? Because true or anything is true. Does that make sense? Once something is true, you cannot use or to turn it around to become false again. So that's why not P or R simplifies to true. Same thing with here, and same thing with the other one. So all of these and true, they simplify to nothing because true is the identity of conjunction. So those are all gone. So now we have the second last line. So now the biggest question is, well, from the second last line to the last line, how does that work? Not P or R, okay, yeah, we figured that one out, we just copy that. What about this not P or not Q? I mean, we can see it's here. Then what about all of these other terms? How did that get simplified? Because the other ones are more general, okay? So when you have two expressions, one is more general than the other one, and they're all inside the conjunction, the more general one can disappear without changing the whole thing. Say that one more time.
I said that and two of them are exactly the same as each other.
Yeah, so these two are the same. Yeah, but still, the or R, is somehow gone, and this one with this one is okay. This one has to do with this one here. Yes.
So is it more general? Do you mean like not here R is more general than not here R or not Q?
Yes. So let me make it more more general. Okay, how that simplification works. So we have A, we have B, and then we have C here. Okay, the truth table would work just like that. Okay, so we have A or B, and then we have A or B or C. Okay, so the question is, nope, this is not what I want. Okay, so we got A, B, and C. I have to think about what I want to say here. So we got A or B and A or B or C. And then we only got A or B here. Okay. So I'll have you guys work out this truth table. Okay. So populate A, B, and C. There should be 8 rows to this truth table because there are 3 independent variables. So you have 8 rows. So work out those 8 rows for A, B, and C. And then work out this expression, which is A or B and A or B or C, okay? And then work out the last column. What do you think you would find? These 2 columns would be the same. Okay? Does that make sense? Now, does it make sense from the perspective of Boolean algebra? Because you can prove this using a truth table, no problem, okay? That is a very concrete way to prove equivalency in Boolean algebra. But you can also prove it using Boolean algebra. So I'm going to prove it using Boolean algebra, but for those of you who want to work this out using a truth table, you can do that, okay? So just look at it as a mini ungraded homework assignment. But it's going to be healthy to kind of be able to do this. So using Boolean algebra, I can prove that too. Okay, so we got A or B, right? Okay. Can anyone dispute that A or B is really the same thing as A or B and A or B? Would that be okay? No one is going to complain about this? Okay. All right. So we have A or B. So now we have to somehow introduce the or C into this, right? Let's see. Nope. Okay, I take it back. Okay, so take that proof back. I'm backing up a little bit. Okay, so A or B is the same thing as A or B, the whole thing, and true. Because and true is always going to work. Okay, what about A or B and true or C? Would that work? Let me see. Is that what I want? It is. It's always true, but in my mind, I'm thinking about, is that going to help me with that thing?
Yeah, 'cause you can distribute it. You can distribute it. You get
Yeah.
A plus B.
So when I distribute, yep.
I was gonna ask, couldn't you just argue that if A or B was false, then it'd be a false across a conjunction on A or B and
Yes.
A or B or C, and then if it's true, then A or B or C is true and A or B is true, so both sides of the conjunction are true.
Yeah, but I'm trying to do it using Boolean algebra. So, so this is A or B as one thing and true. I'll have to think about this a little bit. So I will get back to you. Yes.
For what you had earlier when you had A or B and A or B, can't you just throw an or C in there because the or C won't change anything if it's true or false?
But you have to prove that. You have to use one of the identities or one of the axioms in Boolean algebra to prove that, and I'm missing that.
I thought that was already one, because if you had like A or false is still gonna follow the value of A, just like A or true is gonna follow the same value of A.
Okay, we can get to this one. That's easy. The question is, which rule do we use to bring in the or C?
Yeah. What I'm saying is, like, if you had, A, it doesn't matter if A is true or false. If you have A or false, it still has the same value as A. If you have A or true, it still has the same value as A.
I'll have to think about this one a little bit. But the truth table method would always work. If you work on the truth table, you will see the two columns are the same.
I'm wrong. That's five.
Huh?
A or true would always come true.
Yeah.
Where A is A or false.
Yeah.
Could be both.
Yep. So you have to introduce, an identity here, which is or 0, and then you factor out. So once you factor out, it becomes false or C, and that has to be ORed, after that too. So I'm gonna have to work this out a little bit. But that's the result, of the simplification. Basically, not P or R being here also means that not P or R or T does not have to be there anymore. Because, okay, so if you just look at it from the logic perspective, if not P or R is already true, don't you think, not P or R or T has to be true too? Yes? So that means, this extra term is useless because it is ended with this thing here. Is that okay? So intuitively, it makes sense too. I'm just not, having the formal proof that, this works. But give me a moment after class and I'll be able to work it out. Is that okay? So what is the bottom line? So we are now focusing on the pine needle. So the bottom line is we started off with something that is kind of general, with nested, operators and whatnot, and we ended up with a CNF. Yep.
Does the line before that still count as a CNF?
Yes. So the line before is already in CNF, but it's not simplified. So if I only ask for CNF, the line before is already satisfying that requirement. Even this line is already satisfying too, because 1 is a symbol. It is a constant, so that works too. Yep. CNF is conjunctive normal form. So conjunctive normal form is discussed up here. Okay. So we, so in the new propositional logic system, we only have one negation operator and a disjunction as the only operator. And then we introduce this term of is a disjunctive element. A disjunctive element is basically everything in alpha. is automatically a disjunctive element. So 0 is a disjunctive element, 1 is a disjunctive element. If we have variables p, q, r, s, t, each one is a disjunctive element. The negation of a variable is also a disjunctive element. Is that okay? So once we define what is a disjunctive element using these 2 points here, then we define what is a well-formed formula. So in this particular discussion, let me click here so we can focus on that one equation or expression. So what this expression is saying is, I will give you n disjunctive elements, which is what this part is saying. It's a fancy way to say that using only symbols, but what it says is I will give you n disjunctive elements from phi 1 to phi n. Is that okay? And then I can assert that the disjunction of all those phi's is a well-formed formula. But this is the only type of well-formed formula under this particular method, under this particular definition. Yep.
So that's not really considering like the implicit conjunction, right? You're only
Correct.
disjunctive elements?
Yes. So the well-formed formula are only the disjunctive terms because the conjunction is implicit. Yep. So the conjunction is basically a conjunction of all the well-formed formulae that are known to be true. So are we still doing okay so far? Understanding what is conjunctive normal form? So let me ask you this question. See if you can kind of zoom out to look at 2 trees at the same time. Okay? We talked about resolution. Okay, let me scroll back to what resolution looks like. Okay. So this is one way to look at resolution, and this is the other way to look at resolution. But that's the essence of resolution. Okay? Why do you think it has something to do with CNF or conjunctive normal form? Yep.
Because that's in CNF on the left, so if you can apply that, you can simplify your CNF.
Yep. So if the left-hand side of the implication is CNF, and whatever follows is a disjunctive form, do you think I can add this into the whole big conjunction without changing the meaning of the conjunction? Yep. That makes it a longer conjunctive form, CNF. So that's how these two are connected. CNF is what enables us to apply resolution. Okay? But the result of resolution can be added into the CNF to make the CNF longer and longer. Is that okay or not? I'll give you an example. So let's see. I'm skipping forward a little bit in order to come up with an example. So I'm skipping quite a bit forward here. Okay. So we'll take a look at this thing here. This part. So focus on just this part here. Can we apply resolution? In other words, can we find 2 disjunctive terms where they share a variable, but the variable is negated on one side but not negated on the other side? So let's check it out. And it doesn't look like it, but it does, because P by itself is P or true. P or false, excuse me. Okay, so P by itself can resolve with not P or R. It can also resolve with not P or not Q. So by taking not P or not Q as one, P or false as the other one, I can now resolve and say, oh, we can end up with not Q as the result of the resolution, but the result of a resolution can be added to the conjunction without changing the meaning of the conjunction. It's raining. Is this okay? Okay. Not quite following. That's okay. Let me move this into That's okay. I'm just going to copy over here so that we can, so we have not P or R, not P or not Q. And this time I'm going to have not P or false, and then we have Q or false. Okay, there we go. Okay, so I'm going to block out the other one and look at only this, okay? I'm borrowing multiplication to mean conjunction, and I'm borrowing addition to mean disjunction, okay? So it's just a lot easier for me to type like this, okay? So the question is, can we apply resolution here? Can we find two disjunction terms where they share the same variable? On one side, it is negated. On the other side, it is not negated. Okay? So let me identify which one here. Okay? So we got a not P here, right? And we got a single P here. Okay. So when you look at this and go like, that looks like, it looks like we can apply the resolution rule, because the resolution rule says, if you have the negation of a variable on one side and a non-negative variable on the other side, and they're both disjunctions connected by a conjunction, disjunction connected by conjunction, then we can apply that. So basically what it means is these two expressions will now resolve to a new term, which is the remaining portion of each one, but we can get rid of the shared variable. Is that okay? So the result of the resolution is not Q or false. The not Q comes from the first expression, and then the false comes from the second expression. Is that okay? Is that okay? All right? So, but this term, because it is the result of resolution, because of these two, now we can have a bigger conjunctive normal form, including the result of the resolution, and that would still have the same meaning as the original one. It just looks longer. So now we can now include this one, and you can put it anywhere because it doesn't have to be at the end. So now this whole thing still has the same meaning as that one. It's just a little bit longer, right? So can we apply resolution again? Well, we can apply resolution again because, hey, this guy has Q and this guy has got not Q. Okay? One variable shared between two disjunctive forms. It is negated on one side, not negated on the other side. We can apply resolution. But if we resolve these two, what do we end up with? Well, there's only false on one side, and there's only false on the other side, so we have false or false left, which basically is false, right? So now we can attach this to the entire thing. So once again, I just copy and paste this thing, because, so now I have this entire thing and the result of the last resolution. And they can all be ended, they can all be chained, because the false was implied by, things that are already in the original expression. But then you say, oh, but false or false is just false. And anything and false is false. That means this entire thing is false. Really? We want to make things false? And the answer is yes. We actually want to make things false. Okay? And that's the third ingredient in this whole thing. Okay? But is this part okay? Just mechanically, what is resolution? Yep.
For the or zero thing you did near the start, is that an extra inference you're making, or is that just part of it being a disjunction?
Well, it just makes it meet the format, right? Because if I just have P and Q here, then it doesn't seem to be, they don't look like disjunctions, and when they don't like disjunctions, then it doesn't look like that we can apply resolution. But now that I have introduced the artificial or false, then it becomes a disjunction, and it meets that template requirement that we need a disjunction here, we need another disjunction here. They can share a variable, but it has to be negated on one side and not negated on the other side. So this is just enforcing the format so that it complies with what we visually want to see when we apply resolution. So are we still good so far with the mechanism of resolution? Is that still good? Okay. So now we have the third ingredient. So the whole thing has many ingredients. The third ingredient, you might have encountered this term already. It's called proof by contradiction. Okay, so proof by contradiction is introduced here. So we want to prove proof by contradiction. Nobody is getting that one. Okay, let me say that one more time. We want to prove by contradiction. So we want to know that the technique that we know as proof by contradiction is logically sound. And we can actually do it, okay? So it starts with this, basically is a sub-theorem, okay? By itself, it is not a really important proof, but it is useful. So what are we proving here? All we are saying is this is always true. Okay, what exactly is that? Or, what exactly is this? All it is saying is if you already know that P implies Q is true, okay, assuming that P implies Q is true already, then P and R implies Q and R is always going to be true. That's all it's saying. Is that okay? So, okay, I'll give you an example. If Tech forgot to wear his glasses, then everybody is got an A in this class, assuming that is true. Okay, then it also implies that if Tech forgets to wear his glasses and he's eating an apple, implies everyone in the class is getting an A and Tech is eating an apple. So the and eating an apple part is just like, what does it have to do with grading and forgetting to bring his glasses? Absolutely nothing. But we can attach any conjunction as long as it is done to both sides, then it's good. Okay? Is that okay? Yeah. All right. And then we have this thing here using that particular theorem. So we have psi, then we have phi. Okay? So if I tell you that psi implies phi, okay, don't you think we can apply what we just learned earlier and introduce an extra thing and end it, right? Right? Well, we can just introduce this R here. Except in this case, this R is not something that is totally irrelevant to us. It is actually the negation of phi. But the rule still applies. So now we can say psi and not phi implies phi and not phi. I'm just attaching and not phi to both sides of the implication. Is that okay? We know this is okay because of the earlier proof. But now we have a little bit of an interesting result here because phi and not phi is guaranteed false. Right? So that means psi and not phi is false, implies false. Is that okay? Okay, big deal. Okay, you're just playing with symbols here and there, and then phi and not phi cancels out itself to become false. What is the big deal? Well, the big deal is in the proof, psi is representing everything that you are told that is true. All the axioms, everything that you're told to be true, assumed to be true. That's psi. Phi, on the other hand, is the theorem that you're asked to prove. Is that okay? So proof by contradiction is doing this. You're basically negating the very theorem that you are told to prove. You take the negation of that, and then you do a conjunction with everything that is known to be true, and then you're trying to apply derivations. It can be algebra stuff, can be calculus stuff, can be Boolean algebra stuff, depending on what the phi and the psi are. but you want to get to a contradiction. You basically want to say this conjunction has to be false if phi is indeed implied by psi. Is that okay? I'll give you an example. Because this discussion is kind of abstract, but I can give you an example. It's called the pigeonhole principle. Okay? How many people have heard of the pigeonhole principle? No, you just have to. I mean, it's a fairly well-known principle, not even only used in a class like this. If you have taken some philosophy classes, some logic classes, that's actually a fairly well-known principle. So we'll go with that one. So the pigeonhole principle says this. Okay. So there are n pigeons and m pigeonholes. And you are told that n is greater than m. It is a given, okay? We count it, okay? We look at the number of pigeons, we look at the number of pigeonholes, and n is greater than m. It is a known fact, okay? So after all pigeons return to pigeonholes, then at least one pigeonhole has more than one pigeons. That's one variation of the proof, but it suffices. I mean, the theorem, but it suffices. Okay. Does that make sense? So you can think about concrete numbers, right? You can say, okay, in your mind, you're looking at 5 pigeons, and it's getting dark. There are 3 pigeonholes here. Okay, and the theorem is basically saying at least one of the 3 pigeonholes is going to have more than 1 pigeons. You can try to make it as even as possible, right? 2 pigeons in one, 2 pigeons in one, and 1 pigeon in the last one. Hey, you got 2 pigeonholes with 2 pigeons, which is more than 1, right? You can also go for the extreme cases. Maybe one of the pigeonholes is sheltered and heated. So all 5 pigeons try to cram into that one single pigeonhole. Then you have 5 pigeons in one single pigeonhole. But the bottom line is there's no way to make it so that none of the pigeonholes has only 1 pigeons at the most. There's no way we can make it happen. Assuming the pigeonholes are not elephants. Or the mouth of a monster, right? Then pigeons start to disappear. Okay, so that's the pigeonhole principle. But when I ask you to prove that, how would you prove something like that? It is so intuitive, and yet in formal logic, you cannot directly prove it very easily. So what do? We prove it by contradiction. Okay? So now we have to identify what is phi and what is psi. Okay? Psi is representing everything that is given true. Okay? So what is given true? We got n greater than m. That is given to be true. Is that okay? All right. So now we have phi being the theorem that we want to prove, which is basically saying at least one pigeonhole has more than 1 pigeons. Okay, I mistyped here, forgot about the pigeonhole. So the phi, which is the theorem that we want to prove, is saying at least one pigeonhole has more than 1 pigeons. Okay? So what do we need to do in proof by contradiction? Do you guys remember the flip side of this? What do we need to do when you want to apply the technique? You have to negate the theorem first. Okay? So when you negate the theorem, you have not phi. So how do you negate this? What is the opposite of saying at least one pigeonhole has more than 1 pigeons? What about I say all pigeonholes have at most 1 pigeon? Would that be the negation? Okay. So we say all pigeonholes have at most 1 pigeon. Because some can have none, okay? I still allow that possibility. Would that work? Yes? Okay. So when you want to look at it in a formal manner, at least one pigeonhole has more than one pigeons is using the existential quantifier. There exists at least one pigeonhole such that the number of pigeons in it is greater than one. Okay? The negation of that is using the universal quantifier. It's saying for all pigeonhole, for all x as a pigeonhole, x can only have up to one pigeon. Okay, so I'm just throwing that out here just so that we can relate this to things that we have already talked about. Okay, so now we are looking at psi and not phi. Psi and not phi is basically saying we got more pigeons than there are pigeonholes, and all pigeonholes have at most one pigeon. Why is that a contradiction? Why is that not possible? Well, you think about it, right? So psi says m is greater than n is greater than m. Okay, that's just given to you. What about not phi? Not phi implies the following. What does it imply? Let's check it here. It says every pigeonhole have at the most one pigeon, and we have m pigeonholes, right? So we can only have at the most how many pigeons? We can have at the most m pigeons. Is that making any sense? Okay. There can be at the most m pigeons. And what does that have to do with n? N is the number of pigeons, right? So this means that n is less than or equal to m. Does that make sense? Just logically. Okay, but remember, psi and not phi are ended together. So now we end up with n is greater than m, and n is less than or equal to m. This has to be false. So we have our contradiction. Now, because we have this contradiction, it means the negated theorem cannot be, which means the original theorem has to be true. So this tells us that the theorem, which is phi, has to be true. At least one pigeonhole has more than one pigeons. This is how we prove the pigeonhole principle using proof by contradiction. Is that okay? It's a very powerful proof technique. Okay, we only got about 2 minutes left, so I cannot give you another example. But this is a very powerful proof technique. Some proofs are very, very difficult to do using a direct proof. So you basically start with psi, and then you go forward with implications, implication, 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 until you get to phi. That can be very difficult with some proofs. But proof by contradiction sometimes is very easy on those very same theorems. So it's a very powerful proof technique. Has anyone been exposed to proof by contradiction outside of this class? Yeah, go ahead. Sorry? Number file on YouTube. Oh, okay. Okay, that makes sense. So we'll probably end today's class like this, except we still got 1 minute left. So we're gonna zoom all the way out to the forest. Okay, so 3 trees in the forest are particularly interesting because they're right next to each other. They seem to be related. First one, resolution. Second one, CNF, conjunctive normal form. Third one, proof by contradiction. So we have 3 things that seemingly are kind of not so related, because resolution is like logic, okay? This implies that. CNF basically says, give me any Boolean expression and I can magically make it look like this format. And then we have proof by contradiction, which only seems to have something to do with pigeons and not any of the other topics. So after the exam, okay, we'll talk about the answers to the exam, and then after that, we'll come back and revisit these 3 seemingly unconnected concepts and see how they can work together really well in propositional logic. Yes, sir?
So you said after the exam, does that mean that we'll still have lecture after the exam? Or you
No. Exam, like after the exam, like next Monday. Yep. So there won't be any lecture after the exam. So when you're done, you can leave.
Are we actually going to be running programs of propositional logic, or at least seeing examples of it?
We can consider that.
Okay.
Yep.
You said the exam is next Monday?
The exam is
I thought it was
Wednesday.
Wednesday.
No, next Monday is when we review the answer to the exam.
So it's not this Wednesday, it's next Wednesday.
No, the exam is this Wednesday,
Okay.
and then next Monday we'll go over the answers of the actual exam.
Okay, I understand.
He tried to
Okay.
convince you to make it next week.
Oh, there's always the next week, and then